All right, thank you. It's my pleasure to introduce the next speaker, Laurie Trenery, who is an assistant research professor in the Department of Atmospheric, Oceanic, and Earth Sciences at George Mason University. And with that, I'll let Laurie take it away.
Thanks, Tim. All right. Can everybody see my screen?
We can, but it's not in full screen mode, so it doesn't matter if you're in full screen or not.
Oh, okay. Well, it looks full screen to me. Anyway, hello, everyone. It's great to be here. My thanks to the organizers for inviting me. So this work was done in collaboration with my colleague, Tim Del-Sol. And we were really interested in understanding how we might utilize climate model data to inform our prediction, subseasonal prediction of observations. So just to clarify what I mean by subseasonal timescale and also why it's such a challenging problem. This figure is showing some qualitative measure of predictive skill on the vertical axes and predictive lead time on the horizontal axes. On the far left are weather events.
Laurie,
Yes.
I'm going to interrupt because we can't see anything but your first slide right now.
Oh, really? Okay.
Okay, now we can see.
Huh, it must be the going into full mode. I'll just leave it like this. I think it's the same issue that you had earlier.
Yes.
Okay, so back to my point here. So what is subseasonal timescales? So on the far left, we have weather events, and those are forecasts that are targeting hours to 2 weeks, has relatively high skill initially, and then the skill drops off rapidly at 2-week time period. So these forecasts are often referred to as initial value problems. They get their skill from the initial conditions. And then on the other end is seasonal outlooks or seasonal forecasts. This is typically targeting periods between 3 months and 12 months. They're often referred to as boundary value problems. And as an example, if we have an El Nino that's developing in the tropical Pacific, those evolving SST patterns are associated with well-known atmospheric circulation patterns. So we might expect above average temperatures in certain regions and below average temperature in other regions. And nestled in between those two timescales is a subseasonal timescale. For this particular talk, I'm meaning prediction that's 3 to 4 weeks in advance. So they're often considered, it's a difficult time scale to predict because it's considered too long to benefit from the initial conditions, yet relatively short to benefit from the slowly evolving boundary conditions. So despite the difficulty in making these predictions, there's tremendous societal value. There was a historic heat wave, for instance, that hit the Pacific Northwest, and this map is just showing the temperature anomalies. And you can see that there were 20°C temperature anomalies extending from British Columbia all the way down into Oregon. And associated with this heat wave are impacts across many sectors of society, human life to agriculture and wildfire. So if we can advance our capabilities to make accurate subseasonal predictions, we could minimize the cost of human life and also minimize the impacts to these other sectors in society. So given the societal benefit, there have been initiatives to improve subseasonal predictability. And one such initiative is directed towards improving the numerical models. And there are two main programs, S2S, as Subseasonal, the seasonal project, and SubX. And both were really focused on evaluating the subseasonal skill and operational forecasts, and then using that information to somehow improve the numerical models. And this example, this figure is showing an example of the skill in terms of anomaly correlation for two operational systems on the left and right, and a persistence benchmark in the middle. And you can see that the operational forecast systems are doing better than the benchmark, but the correlations are still between 0.2 and 0.3. So, at best, it's explaining almost 10% of the variance. So there's room for improvement. And so another line initiative is developing empirical predictions. And as Tim mentioned in his introduction, the Bureau of Reclamation partnered with NOAA, establishing the subseasonal forecast rodeo, and they provided forecasts for week 3, 4, 5, 6, temperature and precipitation in the Western US. And here I'm just showing some skill results from the inaugural winners in highlighted in orange, and the benchmark. So that was the currently used operational forecast by NOAA, the CFSV2 and damp persistence. And you can see over the forecast period that they systematically outperformed the CFSV2. So this study really established unequivocally the utility of using machine learning methods to advance our subseasonal predictive skill. And so we're also interested in utilizing some of the same tools that Huang et al. Used, but we're going to take a step back, and we're interested in understanding what processes are contributing to that predictability and how the sources of predictability vary in the CMIP, in the climate models, and how they compare with observations. So to do that, we're going to develop some empirical forecasting models, and we're going to train on and predict observed temperature using the CPC data. And our predictors are only going to be SST. We're limiting our predictors to SST because they're considered variations in SST are likely to make a big contribution to predictability in our target region. And it's easier to understand if we isolate our predictors to one variable. So, and we're only analyzing the period 1982 to 2019. And then we'll develop another set of predictive models that are trained on the CMIP6 data. Again, we'll use the surface temperature data and SSTs as predictors. We're training our empirical forecast models on the pre-industrial control runs. We're doing that to minimize, to take out the impacts of external forcings. These are things like greenhouse gas, anthropogenic aerosols, ozone. And so the values are fixed to 1850. And we're going to concatenate the output from the 13 models that are listed in this table. So we'll have 6,898 years of data to train our model. And then this model will then be used to predict observations. So why are we using the CMIP6 data? Well, part of our goal is to understand what the processes are that are driving subseasonal predictability. And we also then want to compare those processes with observations. And so we know that if we can fit and train a model on the CMIP6 data, and we can skillfully predict the observations, then we know that that skill is actually coming from the dynamical models. And that then demonstrates that the processes contributing to the predictability are consistent between the observations and the dynamical models. So prior to training our models, process the data, so our forecast will only target the months December through February. We do this because that's when we expect the predictability to be greatest. All the predictors and predictands are 2-week averages, and the seasonal cycle is removed from the 2-week averages, so the data are centered. And if for observations, we detrend the data to remove the impacts of external forcing like greenhouse gases. And as I mentioned earlier, we're targeting weeks 3, 4. And so as an example, if we're targeting the 2-week average between December 1st and the 14th, our predictors would be the 2-week average between November 4th and the 17th, excuse me. So our forecast region is the same that was used in the subseasonal forecast rodeo of the Western US. We'll make a prediction at each one of these grid points. We'll have a total of 499 stations that we're making a prediction, and all the data are regridded to the same 1-by-1 degree grid. As I mentioned before, our predictors are SSTs. It's likely that local SST variations as well as large scale variations will impact predictability. So our predictors are constructed in such a way to capture both aspects. So in red and in green, we have our local predictors. So these are individual grid points. And then the blue and the black are representing the Pacific and the Atlantic basins will capture the large scale variations. And in total, we'll have 356 predictors. So to capture the large scale variations, we're going to project the data onto the eigenvectors of the Laplacian operator. This is just another way of decomposing the data into large scale modes. And here I'm showing an example for the Pacific. This is the second and third Laplacian. The first Laplacian is the basin mean. So most of you are familiar with decomposing the data using EOFs. This is just another way of decomposing the data, but it doesn't depend on the data set. So we always have the same basis function and associated time series with each pattern. So it allows us to compare like to like. We'll use a hierarchy of statistical models. So our first empirical model is a benchmark, and it's expected. So the El Nino has the largest impact on seasonal predictability. It's likely to also have a big impact on subseasonal predictability. So our benchmark forecast will be a prediction. It's an ordinary least squares prediction where we estimate our betas by minimizing the cost function listed here. Our y's are the grid point temperatures. And our X, or predictors, is the Nino 3-4 index. We'll combine that with two lasso configured models. The first is a single task lasso. And we're minimizing now to find our betas, we're minimizing a cost function that's similar to ordinary least squares, but we've now included this penalty term. And so this penalty term is included to penalize model complexity. So as lambda gets big, it goes to infinity, these betas will go to 0. And conversely, as lambda goes to 0, this cost function will approach ordinary least squares. And the second lasso model that we'll use is multitask. So in the single task, we're fitting the lasso model grid point by grid point, and no predictive model knows anything about its neighbor. In multitask lasso, we're minimizing a cost function of this form to get our regression coefficients, and this y is now a matrix. So we're minimizing the cost function with respect to all the grid points. So I just want to clarify how we estimate our predictor or regression coefficients and select our lambdas. So we have our benchmark, regression coefficients are estimated from observations. And then we have our two sets of lasso models. So we have an observation trained lasso models. The betas are estimated from the first 18 years of observations. And then we select lambda through a 10-fold cross-validation. And then we have our CMIP6 trained models, and they're trained on, the betas are estimated by training on the CMIP6 data. And then we use the first 18 years of observations to select lambdas. So in this way, the observations are actually informing the predictive model that we've estimated from the CMIP6 data. And all the lasso models are evaluated on the same 19-year portion of observations. So the metrics that we will use to evaluate our forecast and verification data are centered, so the time mean has been removed, and we'll look at the normalized mean square error, which is essentially the variance of the errors to the variance of the verification data. If the mean square error is 1 or greater, that's a bad forecast. And also the correlation coefficient. So we're looking at how well in phase the forecast and verification data are. So now we can look at the overall assessment of these statistical models. So in terms of the average temporal correlation, so averaging the correlation across all of those 499 grid points, and versus each empirical model on the horizontal axes, and then this black horizontal line denotes a 0 correlation. For the lasso models, I did a sensitivity evaluation to see how the performance of the model changed if I swapped the roles of the training and evaluation data. So there are red and blue indicating that the different data were used to train the lasso models, and this was kind of to see how robust the fit was and how sensitive it was to data. And so you can see that our benchmark forecast in an average sense, the correlation is negative. It's not doing particularly well. And then if we look at the observation trained models, they also show a great deal of sensitivity to the training period, as does the CMIP6 multitask. And in fact, the most robust and best performing model was actually the CMIP6 trained single task models. For that reason, we'll focus the rest of this presentation, we'll focus on this particular model. And for comparison, we'll compare it with that when we derive the same single task model from observations. So this now we can start looking at the skill. So the figure at left is, so these are both correlation maps. The figure at left is the correlation map that we get from the CMIP6 trained empirical model. At right is for the observations. The red colors denote positive correlation, which is what we want, and the negative shades denote the blue shades denote a negative correlation. So you can see, looking at the CMIP6 trained model, that there's positive correlations over most of the region, and with the exception of in the interior, and it's close to zero, and there are some negative values. If we compare that with our observation trained model, we see that the positive correlations are kind of limited to the Pacific Northwest, and there's large regions of negative correlation. I performed a field significance test on these two patterns, and I was established that the CMIP6 correlation map is significant, while the observation correlation map is not. So one of our questions was to try to get out what are the processes that are contributing to this predictability. And one way you might infer that is by looking at the relative frequency in which the predictors are selected by lasso. And so this figure at left is showing the relative frequency that each one of our predictors is selected for the CMIP6 trained model, and at right for observation trained model. And you can see that from the CMIP6 trained data model, that the Pacific really has a large number of those single predictive models are selecting some of the predictors from the Pacific, and to a lesser extent, the Atlantic. And if we compare that with what we see in observations, you can see that the predictability is sort of spread, the predictors are sort of spread across all of the predictors. And we believe that this is largely because there was so much more data that went into estimating these regression coefficients, so they're much more robust. In this, when we do our observation trained models, there's only 18 years of data, or 18 years of 2-week averages. So in the first figure that I showed for our results, we looked at the average correlation, and the correlations varied. In a cumulative sense, they were weak. Another way we can look at this is in terms of the mean square error. And at the beginning of this talk, I said if the mean square error is 1 or above, that's indicative of a low skill forecast. So here I'm now showing the average normalized mean square error for our different empirical forecast models. The horizontal line shows the 1, and you can see that all of the forecast models have low skill in terms of the normalized mean square error. Even our best performing model is hovering near 1. So the question that we have then is, if you have low skill because you're fitting these predictive models at each grid point, does that really mean that you have no skill at all? Because we're considering climate, we would expect that if you have predictability, it should be associated with a large scale feature. And so what we're going to do then, when we have a skillful forecast, we want to minimize the mean square error. And so and essentially what we have is a ratio of variances, and we can show that this can be reformulated in terms of an eigenvalue problem. So now we're trying to find the combination of forecasts and verification data that minimize the mean square error across all of our stations. And when we do that, so that's what our Q vector is, essentially finding that linear combination. This is our eigenvector. The gamma gives the eigenvalues, which is the normalized mean square error. And just a quick comment, I know I'm running out of time here, so that these covariance matrices are estimated across the station data, but because there's 499, that would make these covariance matrices 499 by 499. It's quite large. So I reduced the dimension by projecting the data onto the Laplacian operators. So now they're 50 by 50. So associated with each of the, so when we do this decomposition, we're finding the most skillfully predicted large scale patterns. And associated with each pattern is a time series, which we can get by projecting the data onto the eigenvectors. And we can get the regression patterns by regressing the data set onto that time series onto the data set. And we'll estimate significance with respect to a bootstrap. So here I'm showing the normalized mean square error versus truncation. The red line shows no skill. And then the eigenvalues are given in black. And you can see that there are two modes that are well separated from no significance, the no significance threshold. And so we have identified a large scale pattern that is being predicted by our individual models. And so here, what do they look like? And these are estimated from Siemens 6 data. And they're typified by a dipole in temperature that's oriented sort of north to south. And if, for those who are familiar, you might recognize that as an ENSO-like pattern, where we, during winter, we kind of have this canonical teleconnection pattern where the warmer temperatures in the higher latitudes and cooler temperatures lower latitudes. So the next question that we have is, so those results were estimated from the Siemens 6 data. Now, how does that compare to observations? Because that was part of our goal, is to see how that compares with observations. And so I've repeated the Siemens 6 map at left and the observation estimated map at right. You can see they're both characterized by dipoles and temperature, but their orientation is different. So are they in fact different? Because remember, at observations, I only have 18 years of data. So I went back to the climate model data and I picked a random model, the GFDL ESM4, and I sampled it to have the same equivalent size as observations and would estimate these maps. And here I'm showing two examples on the middle and the right. And you can see that the middle pattern somewhat has some similarities to the observed pattern, and the pattern at right is more consistent with the overall Siemens 6 derived pattern. So we can't say that the observation, while it looks different, we can't say that it is in fact different, because it appears that the most predictable structure appears to depend on the data. So now, recall that we had pretty low correlations when we looked at the cumulative correlation. Yes, thanks, Tim. Now we've found this large scale pattern that's predictable. And essentially when we do this eigen decomposition, it's effectively filtering the noise and isolating that predictable structure. And so we have this eigenvector that is going to combine those forecasts to give us that predictable feature. So we can apply it to observations and correlate the forecast. So we're trying to see if the forecast is predicting that large scale pattern. Is that what those individual grid point forecasts is trying to do? We determine that by projecting the forecast and the verification data onto these eigenvectors. And this is the leading component. The observations is shown as a horizontal dash line. You can see that it's much higher if we're looking at this large scale pattern. And then I looked at how the skill compares in the individual models, and I sampled the model data to have the same length as the observations. So for each model, the asterisk denotes the mean of the distribution of these correlations, and the bars are giving the 5th and the 95th percentile. I just wanted to see if they were consistent with observations, which they are across all the climate models. And moreover, the models are consistent with each other. So I'm running out of time, get to my last point, and then I'll open it up for questions. But the idea was we started out wanting to know where the predictability was coming from. We identified these large scale features that seemed to have structure that was similar to ENSO teleconnection pattern. Now we have this time series that's capturing the variability of that predictable feature. And so I can correlate that, or I can regress that the SSTs onto that time series and look at what the structure of the SSTs looks like. And here is the CMIP6 derived at left and observation derived at right. And you can see that the feature that really jumps out at you is the SST anomalies in the Pacific. They look very ENSO-like. And so we can conclude that, and these are features that are robust and similar between the two data sets. So with that, I will go ahead and end my talk because I'm already going over, but hopefully you see the utility of using the CMIP6 data to train predictive models and to predict observations, and then also how if we isolate this large scale patterns, we can enhance our predictability. So thank you for your attention.
All right, thank you, Laurie. Unfortunately, we are out of time. We don't